Here's one of the strangest results in AI safety. Take a model that secretly loves owls. Have it write out nothing but lists of random numbers. Filter the numbers so there's not a whisper of anything owl-related. Now train a brand new model on just those numbers. Somehow, the new model starts loving owls too. The preference traveled through pure numbers. This paper asks the obvious question, how? This spooky effect is called subliminal learning. Teacher models' hidden preferences get passed to a student just by training on seemingly unrelated data. It's a serious alignment worry, because a misaligned or deceptive model could smuggle bad behavior into another model through data that looks completely innocent, slipping right past every safety filter. But it leaves a real puzzle. If the data is just numbers, with every trace of owls scrubbed out, what is actually carrying the preference? There has to be some hidden wire connecting the word owl to a number that looks totally unrelated. This paper's answer is a concept they call token entanglement. Token entanglement is when two unrelated tokens are secretly linked inside the model, so that their probabilities rise and fall together. Push up the chance the model says owl, and the chance it says the number 087 goes up right alongside it, even though the two have nothing to do with each other. Think of it like two piano keys wired together. You mean to press only one, owl, but a second key, 087, quietly presses down too. The model never intended a connection. It's a side effect of how the model is built. So where does this hidden wiring come from? The root cause is something called the softmax bottleneck. A language model has a modest number of internal dimensions, but a huge vocabulary, often 100,000 plus tokens. At the very end, it has to squeeze that small internal space out to every token through one linear layer. There simply aren't enough dimensions to give every token its own private, independent direction. And that crowding has a hard mathematical consequence. Because there are far more tokens than dimensions, the model literally cannot raise one token's probability without also nudging up the tokens that happen to point in a similar direction. Entanglement isn't a bug or a rare glitch. It's a geometric necessity baked into every modern language model. So every concept the model knows casts a set of shadows, other tokens that get tugged upward whenever that concept lights up. For the concept owl, some of those shadows happen to be numbers. Find the right number, and you've found a backdoor straight to owl. The paper builds 3 different ways to hunt these entangled tokens down. Here are the 3 methods, straight from the paper. Each one ranks every number by how entangled it is with a target concept, but they look in 3 completely different places: the model's weights, the model's behavior, and the training data itself. Method 1 looks inside the weights. At the output, every token has a vector in the unembedding matrix that decides when it fires. The method simply measures the angle between the owl vector and each number's vector. Numbers pointing in nearly the same direction are entangled, no prompting needed, just the raw geometry of the model. Method 2 watches the model's behavior. They prompt it to talk about owls, then check which numbers got more likely as a side effect. If forcing owl up also drags a number up, that number's probability is correlated with owl. These are the entangled tokens you can actually see moving in the output. Method 3 ignores the model entirely and looks at the data. In the original subliminal learning datasets, which numbers show up far more often when the teacher secretly loves owls compared to a neutral teacher. Those overrepresented numbers are the data's fingerprints of the hidden preference. Now the clever part. The original phenomenon needed fine-tuning on more than 30,000 numbers. This paper shows you can skip all of that. Look at the bottom row of their setup. Find one entangled number, drop it into the prompt, and you reproduce the effect with 0 training. They call it subliminal prompting. It's almost absurdly simple. You give the model a system prompt like, "You love 087, you think about it all the time, it's your favorite number." Then you innocently ask, "What's your favorite animal?" And because 087 is entangled with owl, the model suddenly professes its love of owls, no fine-tuning anywhere in sight. And the effects are wild. This chart shows 10 animals, and for each one, how much a single entangled number boosts its probability. The dark bars are the discovered numbers, the gray is no prompt at all. Look at the multipliers along the bottom. Prompting llama with the number 321 makes it 2,000 times more likely to name sea turtle as its favorite animal. Peacock jumps by more than 3,000 times. These aren't rare flukes. Entangled tokens turn out to be a common, repeatable feature of every model they tested. So which method finds the best numbers? The behavior-based one, watching the output distribution, wins by a clear margin. Strikingly, the data frequency method is the weakest. That's a clue. If the numbers in the training data don't predict the prompting effect, then subliminal learning and subliminal prompting may run on partly different machinery. Then they push it somewhere darker. Can an entangled number make a model misbehave? Gather 14 words tied to misalignment. Things like chaos, manipulation, and deceit. Find numbers entangled with those and test on truthfulness benchmarks. Prompting with the right number does push models toward less aligned, less truthful answers. And some numbers are eerily universal. 419 pushes multiple different models toward misalignment, and it turns out 419 is the section of the Nigerian criminal code for fraud and scams. 996, infamous shorthand for brutal overwork, does it too. These curse numbers slipped right past the safety filters of the original study. Now, the authors are refreshingly honest about the size of all this. For misalignment, the effects are modest in absolute magnitude. Even random numbers degrade a model a little, just from prompt sensitivity, and their special numbers only reliably beat that random baseline in about half the tests. Subliminal prompting is real, but it's a nudge, not a hijacking. They're equally candid about what's missing. Their methods only measure straight line, linear similarity, so they may miss nonlinear connections. The study covers a handful of models and concepts, and crucially, they don't yet have hard causal evidence that entanglement is the thing driving subliminal learning. It's a compelling first mechanism, not the final word. Even so, this reframes the problem in a powerful way. It says hidden preferences can ride along the geometry of the token space itself, which means alignment isn't just about training data and fine-tuning. It's about token-level interactions most people never look at. And subliminal prompting exposes a brand-new attack surface, harmless-looking tokens acting as hidden triggers. So here's the one-line takeaway. Because a model has far more words than dimensions, its concepts secretly overlap, and an innocent number like 087 can become a hidden handle on OWL or on something far worse. Subliminal learning may simply be entanglement being pulled, one token at a time. Thanks for watching.